Hello everyone, and welcome to the MATLAB and Simulink Robotics arena. Today we're going to talk about MATLAB Apps with ROS. I'd like to introduce Cameron.
Hi everyone, I'm Cameron Stabile. I'm part of the engineering development group and I have an interest in robotics, so we'll be showing you some of the stuff I've been working on for the past couple of weeks.
Awesome. Yeah, thanks for being here today. Cameron's put together a really cool MATLAB app that interfaces with the robot operating system, so if you're interested in either of those two sides, definitely watch the rest of this video. So on today's agenda, we'll be looking at the following things. Just a quick recap on the relationship between MATLAB, Simulink, and ROS. We'll look at some examples of how we can use MATLAB Apps, specifically Cameron's app, with ROS, and then we're going to jump right into the software demonstration. We've got a lot of cool stuff to show you today. And then wrap that up at the end with key takeaways. So you might have seen this from the previous videos we've done on ROS. This is really showing that in a typical ROS robotics workflow, you might have different simulators or hardware that are talking to these software pieces called nodes. And once you bring MATLAB and Simulink into the mix, that lets you similarly connect to ROS to perform typical tasks like controls, perception, planning, and decision making. But the focus of today, because of the apps, is going to be on user interaction. So what are some of the user interaction things that we're going to see?
So some of the things that we want to do when we're working with ROS is being able to control hardware. So we want to be able to set up both publishers and subscribers, and we want to be able to interact with those. And typically in a MATLAB workflow, you're doing that by hand, or maybe you have a script. But what's nice about App Designer is that you can package all these scripts or hand code into basically callbacks. So they're much easier to work with once you have it written.
Cool. And you'll see exactly what this means in just a couple minutes. So what's cool about the app that you made, Cameron, is that it works in kind of different scenarios. So the three scenarios that we're going to show you are roughly like this. So first we're going to talk about using a MATLAB app to communicate directly with a robot. So here, you have MATLAB running on your desktop, and then you might have a robot running ROS, either on the same computer or on a different one. Because MATLAB has a ROS connection, you can just have this app, like you said, set up publishers and subscribers to get sensor data or send velocity commands to the robot.
Right, and one of the nice things you can do with that is you can visualize this data directly in MATLAB. So basically you can encapsulate all the things you need, bring them into the MATLAB environment, and both view and work with that data there.
Yeah. So then, we decided at some point manual control, we can all do that. So what if we also have an autonomous algorithm running on this robot, and we decided to implement that in Simulink? So we actually took a Simulink example and modified it to do waypoint navigation and obstacle avoidance. So then we're able to use both MATLAB and Simulink on our desktop, so that we have the app that's basically acting as a visualizer or manual controller. We have a Simulink model doing the autonomous control, and then everything's just communicating together using ROS.
That's right. And so we have this model running on our host computer. We also have this MATLAB app running. And as you know, MATLAB is single-threaded, so in certain circumstances, or if your hardware isn't that robust, you can generate C++ code and deploy it as a node to the ROS environment, basically offloading some of the computation and speeding up the overall operation of your app and executable.
Yeah, and I think that's the next example, right, where, again, we take the Simulink model and put it on the robot, and then, once again, MATLAB is just dedicated to running that app. So as we go through the examples, we're going to see kind of as we step from the first to the third example, and we're going to see this also where our robot is both simulated and real. I think we're ready for the software example.
Sure. Okay, so now we're going to do a little bit of a software demo. We'll start by just opening App Designer on the app that we've created. So after this loads, basically what you'll see is the user interface, which has all of our visual buttons and UI controls. So I'll show the layout once we actually run this, but you have both the design view, which is a very easy way to just move objects around and kind of configure it the way that you visually want it to look. And then you have the code view. And in here, a lot of these callbacks, functions, and properties can be generated with the click of a button, and then you just fill it in with the code that you actually want to run when that callback is executed.
One thing to add, Connell and I have done a video in the past on App Designer, so if you want to know more about how you can set up these kind of apps, do check that video out.
So what we'll do now is we'll run this app. So it's going to open, and we'll adjust it slightly so it fits on the screen. And so the basic design of this app right now is you have sort of your connection information to the ROS device in this top left corner. Below that, you have the waypoints that we'll be sending to our Simulink model, which is doing the autonomous navigation. But we also want, in a lot of cases, to be able to control the Turtlebot, in this case, or whatever robot you want to connect with some manual controls, whether it's to reset its position or whether it's to, move it out of a tight spot when the algorithm is not doing what you want it to. So we've added a bunch of buttons and features down here so that you have that control as well. In the top right, we are visualizing some of the data that we're generating in MATLAB, such as the waypoints and the position of the robot. In this case, we're not connected, so it's just at the default position of 0, orientation 0. But when we connect to ROS, we'll also be getting information like LiDAR, odometry data, and also point cloud data, and in addition to that, camera views. And in the bottom right, we have a changeable view for the LiDAR, camera, and point cloud. And this is just how we've configured it. If you have different sensors and want to bring in other data, it's as easy as going into your app designer, creating a few new buttons and callbacks, and displaying it however you want to. So what we'll do now is we'll connect to ROS. You'll see that I've created basically edit boxes which bring in the model that you're working with, the IP address that you'll be connecting to, and this is just a box that tells you what target you're going to be running your model on eventually.
So that's if you're either simulating it on your desktop or you're running something that you've already deployed.
That's right.
The robot, yeah.
So we'll connect to ROS. This will pause a sec. We see that we're connected now, and we actually see that our model has changed slightly.
Yeah, so where is the robot actually?
So right now, if we go to our gazebo simulator, we have, this is our X direction, global X, this is global Y, up is Z. So right now we're sort of pointing up towards Y, and we see that here. Let's say that just to begin this, we reset the odometry. So this button essentially just zeroes out the robot's position and orientation, and it also, because we're working in gazebo, makes it so the robot returns to center with that orientation.
And that's just a ROS service you're calling, right?
Right.
From MATLAB. Cool.
So at this point, we're getting LiDAR information. If we want to change the subscriber that we are viewing, we can change it to the camera. So now we see what the robot is seeing, and we also have the ability to change the point cloud.
So this point cloud was a fun one to get working because point clouds there's a lot of data. So there's a couple of things that we did, I guess, to try to get this working better. The first one was that you basically set up a kind of a rate limiting on how often you plot this data, right?
That's right.
And then,
so that was the initial way of sort of limiting the processing that needed to go on. This is refreshing at something like 0.05 or 0.1 second.
Yeah.
This has to go quite a bit slower, not to mention the fact that the point clouds are being published at a slower rate as well.
Yeah, and then the other thing we added there was, if you see at the bottom right, we have the point cloud downsampling. So here's where we're reading in our point cloud into a format used by our computer vision system Toolbox, and that gives us access to some of the downsampling functionality so that we're just displaying less points. And that helps a lot. So these are things that you should consider when you're working with these large point cloud data. So keep that in mind.
Yep. So that's the majority of the visualization. I guess we also have one other thing we can show, which is if we go to our LiDAR view, you don't need to be in the LiDAR to see this, but we can overlay what our the LiDAR scans onto our top plot, and we can increase the history. And then from here, maybe what we can do is we can show some of the manual controls. So in this case, we are just sending direct base velocity controls, and we can do that using this keyboard control, which brings up a small window. Basically, you just need to have this in focus to move the robot around. But now if you view the top right plot, you'll see that we're moving the robot just using our W, A, S, and D keys. And, you know, I chose to do this as sort of using a tan H velocity curve. But you
just
can
to get that
choose
smoother, right?
Yeah, so but you can choose, you know, you can do this however you want.
Yeah, and I noticed that the scans, you know, they're not lining up perfectly.
That's right.
That's because the odometry is drifting, right?
Right.
So usually when you do this kind of stuff, there are functionality for lining up or matching the scans. So if you're interested in that kind of stuff, you should reach out to us too.
Right, and there's one other thing, which is that the faster your hardware is, the more the scans line up, because another thing that's happening is the timestamps aren't actually matching up, and you can add your own sort of logic into your plotting loop to match those timestamps if you want to add that.
Awesome.
So we'll close this manual control out. We'll reset our odometry. Okay, and I guess the next thing we'll do is we've put it into manual control for the time being. So when we run this model, we shouldn't see anything happen, which is sort of what we want. So let's run this model.
And that's going to load the model, the name that you specified.
Right.
On there.
That's correct.
So I guess the model's loading.
So the model's loading. It's compiling a few elements of the model. Once it finishes updating, it will begin running. Once it does, we'll see this this lamp turn green, and then we'll know that we can either control it ourselves or put it into this autonomous mode, and it'll go and track these waypoints on our plot.
Yeah.
Okay, so at this point, our model is running. We still see that we're updating our LiDAR information. We'll reset this to show our camera. And what we'll do first is we'll just show that we now have access to these sort of set rate controls. So if I just tell it to go forward a little bit and turn a little bit to the left, it will go into this obstacle avoidance mode. So in this case, we have gotten to a certain distance and we're not trying to turn, we're just trying to move forward, so our robot just doesn't go anywhere.
And can we see what that looks like in the model? Because one of the things, so when this model is running, if we go inside the motion planner, we basically developed our entire logic here using Stateflow, which is our state machine logic authoring tool. And what's cool about Stateflow is, well, first of all, it lets you model algorithms graphically. You can do some pretty complex stuff, like in here. So you'll see what's highlighted here on the bottom left is this manual mode state that's in blue. So that's saying that we've set the mode of operation to manual mode. And that's why, you know, only the commands that are inside that state are running. You'll see that it's basically running this obstacle avoidance function and this speed control manual function, both of which we've defined kind of at the top level of this chart. So obstacle avoidance is using some of the built-in robotics system toolbox functionality, and then speed control manual is basically a flow chart that just accepts the speed that we give it unless obstacle avoidance kicks in.
Right.
So then I guess if we switch it to manual, then we'll see how this logic also is affected. Right.
Right. At this point, how about what we do is, so it broke out because we had a tiny bit of rotation, but let's reset our speed, and let's also reset our odometry. So in this case, we're just going to return back to the origin. Mm-hmm. And now, rather than doing manual mode, let's go and do automatic mode. So in this case, we're going to see this robot try to track these 4 points.
And those 4 points, you set them up in that waypoints table, right? So
that's right. So, you know, we've added a few neat features, such as having the robot tell us which waypoint it's tracking right now. So here we see that it's obviously tracking the first point, but once it gets close enough, some element in the state flow chart will tell it that it's reached its goal, and it'll move on to the next point. All the while, we have obstacle avoidance in place, so if it turns into, or if it reaches a situation where it's too close to an object, it'll stop and it'll start turning. If it basically is surrounded, it'll go into a recovery mode. And if it just senses a objects to one side or another at a higher distribution, which it uses the LiDAR scan object for, then it'll just shift its orientation slightly so that it kind of skirts around to the less occupied side.
And what I think is super cool about like the way this app and this model work together is that you've set it up so that you can change the waypoints live as this thing is running.
That's right. So right now, let's say that we have this fourth waypoint, actually that's covered by the top marker. Let's talk about the third waypoint. So right now it's 6, -3. Let's just change that to 6, -2. At this point, what we can do is we can click off it. You see that it's changed over here. We can publish this, and we can just restart the waypoints. And from there, the model should go back into tracking the first waypoint.
Yeah.
And after that, it should follow the new waypoint that we have here in the third place.
Awesome. And then we'll see the obstacle avoidance try kick in here.
Right. So you see the obstacle avoidance goes active. It's decided that it wants to go left.
Perfect. And then it goes around the bookshelf. Awesome. Yeah, and you implement the waypoints as it's a parameter on the ROS parameter server, right? So that's just updating whenever.
Yep. So the server updates with the active waypoint, and the waypoints themselves are published as a pose array.
Awesome. Cool. So yeah, that's a pretty impressive model and app. I think, we're talking a lot about the modularity of ROS. We can also show the app working with a real Turtlebot with just a couple changes.
So now we're working with the Turtlebot hardware. We see that we're receiving information. So we have LiDAR, camera, and point cloud. And to get here, basically what we did was we changed our IP address. We modified some topic names. So in this case, the Turtlebot hardware uses a different ROS topic for the point cloud. For the ROS VM, it's camera depth points. For the Turtlebot, it's camera depth _ registered. So we changed that, confirmed it, and connected.
And then that's where, if you have a different robot or you want to get rid of some of the topics, you can change that yourself there.
Right. So now here we have our Turtlebot viewing our hallway. We'll publish our waypoints and restart it, which will tell the Turtlebot to start the first one and run the model.
And then you'll see that the target now is set to deployed, which means that the Simulink model is actually on the robot.
Right. And to do that, we go to app configuration, simulation target, deployed.
Cool. So I noticed once, before while the model's running, you started off in manual control so it doesn't just run off.
And so now we can change it to automatic.
Yep. And then you'll see the robot should be taking off. You see the camera image updates, and maybe you might see the obstacle avoidance green light coming on at some point. There it is.
So now it's avoiding that right wall, headed towards the first waypoint.
So let's follow the robot here.
All right, so thank you for showing all of those demonstrations. Hopefully that gives all of you a good idea of some of the stuff you can do with MATLAB Apps and the Robotic System Toolbox's interface to ROS. We just want to wrap this up with some key takeaways. The first one, as Cameron showed in great detail, is that you can build apps using App Designer, and this lets you lay out all sorts of different components like tables, user controls, plots, all within an app window. And in conjunction with that, we have the ability to communicate between MATLAB, Simulink, and ROS. And on the MATLAB side, that could be a script or a function, as we've shown in previous videos, or in this case, it could be an app. And finally, that modularity, both in MATLAB and Simulink, but in ROS, makes this pretty useful. Some of the things that we saw were, first of all, that the Simulink model, you could run it in your desktop or deploy it as standalone code on your target machine. And secondly, just because of how ROS works, we could easily, just change the IP address, change the topic names that we're connecting to, and then we can use the exact same algorithms, the exact same apps on a completely different platform. Yeah, so thank you for showing us this.
Yeah, my pleasure.
And the files are going to be available on the File Exchange,
That's
so
right.
You'll see the download link in the description below. to finish up, we always show you these resources. If you want to know more about the apps or ROS or anything else, you can reach out at roboticsarena@mathworks.com or get in touch on our Facebook group. And again, feel free to check out the other hyperlinks here. So thank you for watching.